On to part 3 of the time part of this course. And so we're now going to deal with absolute age dating. And what you see here is a crystal of zircon. Zircon's one of them, I guess you might call it a preeminent sort of mineral in as far as age dating things. Now, it's a ZR SO4, I think it is, SiO4. So it's a silica mineral. And being an SiO4, it's kind of related to olivine. Olivine, as you probably know, has both iron or magnesium in its structure, but this one instead has zirconium. And so because of that, as you know also from Bowen's reaction series from Geology 100 or 110, that Bowen's reaction series, these SiO4 minerals tend to form first from magmas. And so zircon tends to form early on. And it also tends to have a lot of uranium in its structure as well. And so that uranium, regardless if it's uranium-235 or 238, can be used then to do age dates. Now, most of the crystals that you'll see with zircons like this are not that big, and they tend to be you can find them either in volcanic rocks, usually in felsic igneous rocks, or in granites, and or in volcanic ashes, or things like a rhyolite. Those are the most common ones that tend to have a lot of zircon in them. And then also, once you weather those rocks, they're going to be involved in many of the sandstones. And then you can actually do age dating on detrital zircons and at least get some limits or at least some idea of where the zircon came from. So zircon is a super mineral, and you'll see that shortly here. So up to this point, we have a geologic time scale, but we don't have anything other than relative age dates. We have a geologic time scale, but there are no numbers that we can attach to it at this point. What is that sort of history that people had? What are the numbers that people would attach with the age of the earth, or the age of man for that matter? And so, and a lot of that in the Western tradition stems out of the Christian church, actually the Catholic Church, and even beyond that into today, into more evangelical sort of traditions. And so they would say that, in fact, the earth is only 6,000 years old. That seems to coincide with some of the earliest writings that we have that are of, from antiquity, whether you're in the Eastern or Western traditions. And so history began to develop when people came out of the caves, or people left Africa to inhabit Asia, and then Australia, and then also North America, and then across into Europe and so forth, and stayed in Africa for that matter. And so the idea is that these traditions are pretty skeptic. You have to be a skeptic of most of these things. So the earth is older than 6,000 years. I got to tip my hand now and tell you that. But anyway, where did that number come from? In the next slide, you can actually see the guy's, a photo of a painting of Archbishop Usher. And Usher was actually around 1658. So he was actually a Protestant. He was Anglican, I think, in fact, and he was an archbishop in the Anglican Church. And so he made calculations based off of his understanding of the manuscripts that were used to compose the Bible. And in his argument, he came up with an actual day that the earth was created, and that would have been October 23rd, 4004 BC. And so it was a very convenient sort of idea that numbers mean something in Christian faith. And so 1,000 is one of those sort of magical years, because nobody lives to be that long, right? So nobody's 1,000 years. And so those are the sort of ages that people dealt with. And so the creation, of course, only took place in 6 days. The seventh day God rested. And on the, after that, there were about according to a hypothesis, okay, let me put it this way. It's like, I think it's one easy to disprove, but there's a dispensational sort of hypothesis that Christians have that it was 2,000 years between creation and the great flood, the Noah flood. And then 2,000 years from the Noah flood to the time of Christ. And then, of course, it's been another 2,000 years since the time of Christ to where we are today. Our calendar is based off of that event, if you will. And so, before Christ, or Anno Domini, which is after his birth. And so the, it's a huge imprint on the human consciousness to attribute things to things that we can understand, numbers that we can count easily. So what are the actual age dates and how do they compare? Okay, before we get into that, there are other traditions out there. Okay, so on the left-hand side, you can see creation here, and that's the Garden of Eden. I forget whose version of Garden of Eden that is, but it's not the Hieronymus Bosch version of the Garden of Eden, but unicorns and all that sort of thing that are around in the garden. If you go to the next slide, there are other sorts of philosophies that propose origin myths. And even Native Americans had their own origin myths. For instance, human beings a woman came from a beaver, and a man came from a snail, essentially, in the Osage origin myth. And so the origin of people. And so the origin of people and the origin of earth pretty tightly linked in the Christian sort of dispensational sort of like hypothesis, or the young earth hypothesis, if you will. So the Greek philosophers had a different idea, and so they were some of the earliest thinkers that we know of, and they had the earliest philosophies that proposed, and these would be the pre-Socratic philosophers. So Socrates was kind of like the high water mark of the beginning of Greek Western philosophy, and so his student was Aristotle and Plato, and that sort of succession of philosophers came after Socrates. But the Greeks actually felt that the earth had existed through, forever, that we're just on a continuum because people live and people die. And so there's this continuum. And so they had no concept of the end time so much as the end of their own lives, which they were fully aware of. And so the Greek philosophers, it always existed, that it always would exist. And then, of course, the world could be a long time too, right? And they thought that the earth was relatively flat, except for Aristophanes, who was also Greek. And he was Ptolemaic Greek in Egypt, and he recognized that the earth was round, in fact, and he was pretty close. He was pretty accurate in his predictions. And it was a very clever way in which he went about to show that the earth was round. So the Christian faith kind of stuck us with a few myths that were difficult to dispel until we got into science, okay? And so when science helped to get rid of some of those sort of myths that we carry with us. So you can go to this website, Wikipedia, for creation myths, and you'll learn more. It's probably been expanded upon since I last had read that. But it's just nice to know that there are other traditions that are out there other than the one that I kind of grew up with as a child, and had to work my way through that sort of brainwashing that you get as a child. So if we go on to the next slide, and I got to tell you, even the early scientists had this imposed upon them. It's like, if you challenge the church, they would punish you. And so that happened to Galileo. It would have happened to Copernicus, but he didn't publish his things until he was on his deathbed, essentially, or right after he passed away. Many early scientists actually wouldn't have their stuff published until after they passed away because it was regarded as too heretical. And so, but people began to question things, though. They did question things. And so Galileo was forced to say that he had made a mistake, blah, 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 saying that he was following the Copernican system, that, the earth is not the center of the universe. In fact, the sun is the center of the universe. At the time, they didn't even really know what a universe was back then. It was a solar system, what he was referring to. And it wasn't until much later that we even found that, that the earth, the solar system itself is part of one. of a whole series of galaxies that are in our universe. 200 billion of them and 200 billion stars in our galaxy. So with this kind of underpinning, and the strong influence of the church, and they were the most learned people at the time as well. So many of the scientists actually came out of the tradition. They were constrained by the sort of things and their patrons and what they could publish, because they did not want to be regarded as atheists at the time. That was considered a real no-no, and they could burn you at the stake and that sort of thing. And so you could lose your life very easily in that sort of environment as a scientist and speaking your mind. So as science progressed, however, they began to propose different ways to try to figure out the actual age of the Earth. And so one of those ideas was proposed by Charles Lyell. Charles Lyell was the guy who wrote the first geology textbook, Principles of Geology. And he wrote that back in the early 1800s. And he proposed that it's like, well, you could take the evolutionary rates of fossils, perhaps, and calculate what the age of the Earth is. And he calculated roughly, from his understanding of the fossil record, about 80 million years. And of course, we know that fossils actually are present, in roughly about 600 million years. Okay, so he wasn't too far off. It was about an order of magnitude, I guess you could say. But there's some bad assumptions, of course, that he was confined, constricted by. And so that's probably not a very good way to come up with an actual record, because we really don't know how long a certain species lives. You could do the same thing with sedimentology. And you can see how thick is this layer, how thick is that layer, and then you make a basic assumption. It's like, oh, this layer, if it means it's 1,000 years, and you stack them all up, and then you add everything together. And of course, that situation, of course, is flawed, as you well know. I've already shown you photographs of more than 10, 12,000 feet of Cambrian age rock in the Great Basin, and the Cambrian itself only spanned about roughly, 541, so 40, 12, 50, 53 million years, and you get 12,000 feet of sediment, or 4,000 meters, let's say. You get the idea that there's a lot of assumptions that go into this as well. What's the depositional setting, all that sort of thing. And so it has to be marine setting and everything like that. So sedimentation wasn't a very good way to make a rate as well. And we know that you can get, 20 feet of sediment in some situations in an instance with mass wasting events. And then you can have slow sedimentation that could take thousands of years for just a few millimeters of sediment to accumulate. So next was Edmund Halley, who came up and proposed this idea. He says, well, we can measure the salinity of the oceans. We know that the salt has to come from somewhere. It must come from the weathering of the continents. That's where you get all these ions that go into solution, essentially, and they get carried off into the ocean. So they must accumulate in the ocean, and the ocean must be getting saltier and saltier and saltier through time. Using that as his rationale for estimating an age of the Earth, he came up with something around, actually, he didn't do it himself. Jean Joly came up and used that technique, and he estimated about 90 million years, which is conveniently close to what Lyell had proposed anyway. And so these guys were all trying to get around that sort of figure in order to make their understanding. It's easier to sell an idea if it's not drastically different from somebody else's, right? So John Joly proposed 90 million years based on the ocean salinity. We know that's a flawed concept now, because ocean salinity is actually related to the scrubbing in the ocean crust of the salts from that crust. And so you get actually salt deposits in places that have vents and sort of like submarine, they're not really eruptions, but it's like hydrothermal systems in the ocean floor. Actually kind of scrub the salt out. And so the salt in the oceans has actually remained pretty constant over the last 500 million years. And that is known from a technique known as fluid inclusions. And so fluid inclusions in carbonates indicate that it's roughly the same salinity today that it was back in Cambrian time. And that's that the general oceans are well mixed. So the next one was a cooling rate. So there's this idea in physics, if you were to take an iron ball, let's say, and put it into a blast furnace, essentially, but not hot enough to actually melt the iron, or you may get it red hot, right? You've probably seen blacksmiths who take a horseshoe out and it's glowing red and yellow first and then red, and then slowly it'll cool and cool and cool and finally become iron color, right? And the heat that's given off from whatever it is you've pulled out of the fire, that's called black body radiation. And so black body radiation, if you say that the Earth was molten rock at some point, and we took it out of the fire, or we quenched those fires, if you will, and let it cool, if we measure the temperature of the Earth today, it's going to be some proportion to what the original heat of the Earth was. And so you measure the heat of the Earth today, and you can do that with a thermometer. You can dig a hole and take temperature all the way down, and that way you get rid of the seasonal fluctuations in temperature and so forth. So you get an average as you get farther and farther down below. Of course, he didn't know about the geothermal gradient at that time, and he didn't know that the Earth was molten in the center still at that time. His estimate, however, this is Lord Kelvin, William Thomson was his given name, and he calculated somewhere between 24 and 40 million years. And so those assumptions, of course, are flawed because they did not understand the structure of the Earth, let alone what the Earth was composed of when you get below the superficial sorts of materials that are here. You fast forward a little bit in between in the early 1900s and then maybe the late 1800s as well. Henri Becquerel was a chemist, and he recognized for the first time that you could shoot a beam essentially at a target. He worked with cathode ray tubes, and he saw that radiation occurred. And so you can see that there are certain materials that have radioactive properties, in other words. And so Henri Becquerel discovered that, and Madame Curie went on, as we've already talked about her, that she went on to concentrate radium out of pitchblende, and she discovered also that this was a radioactive substance. In fact, it probably killed her. She had a little amulet that she carried around, a little like a locket that she carried around with her, and I think it's been reported that she had like a rash on her chest from where that locket was. So I have photos of all these folks that were in here and part of this story. And so because of Henri Becquerel and Marie Curie, Claire Patterson was the next person in this saga who said, there's a lot of uranium, and we know the average decay rates for uranium at that time, they did. And he says, what if I took the igneous rocks and I could separate out what we think is the age of crystallization, some of these older rocks, maybe I can figure out exactly what the age of the Earth is from that decay curve. And so he did that, and he kept getting bad results. And he would come up with worse and worse results all the time. And in fact, he was doing his work in the 1950s and 1940s. And that's Claire Patterson on the end there. And so Claire Patterson discovered also that there's like, oh my God, there's all this lead that's in the air. And he knew that that was the end product for uranium decay. But there's all this lead that was in the environment. And he says, where does this come from? And of course, it was obvious where it came from. Lead is what they used to put into gasoline when you had an internal combustion motor in order to keep the valves from knocking. It was a type of lubricant that was put in as a compound into gasoline. And that's why we drive around today with unleaded gasoline. It's due to this guy right here. And so there's a book that was written about him. I think it's called Toxic. I can't recall what the name is. I'll put a list of books up at the end of this lecture to show you some of the readings that went into like the discussion of the folks that we've talked about. So anyway, Claire Patterson, we can thank him for not only cleaning up the lead out of our environment, because he actually testified before Congress and he helped get passed in Congress in the 1968, 69, 70, in that era. I think it was 1970. But the Clean Air Act went into effect during the Nixon administration. And it was 1972 that people started driving unleaded cars for the first time that had catalytic converters to take some of the contaminants out of the gasoline. I guess the burned gasoline. So catalytic converters were needed in order to burn unleaded gasoline. And so Claire Patterson, we can thank him for cleaning up the atmosphere in 1971, I think it was. And then 1972 was the Clean Water Act, also during the Nixon administration. And the reason all that happened probably was because of Watergate, and what is so incredibly unpopular that people, the environmental movement, it was just getting its grassroots activities going right then. And so they were able to get this thing pushed through, thank goodness, because it made a big difference in the United States, in the pollution that we have. And we're better today than we've ever been in the in the recent past anyway. Of course, before automobiles were around, we didn't have quite the pollution, except there was coal dust and all that soot and everything from the manufacturing that was going on in the United States. Of course, we don't have very many plants that actually produce that much in emissions anymore today. We have some, however. So Claire Patterson testifies before Congress, says we got too much lead in the atmosphere. He developed the first clean lab, which had positive pressure in it, so it kept it from being contaminated by atmospheric lead. And so what he was able to do was to separate how much actual uranium was in it, and then the actual daughter products from the decay, that lead that was still in the rocks. And so he came up with some of the first age dates, and he knew he couldn't trust any of the Earth materials because of this exposure to lead in the atmosphere and in the environment, right? So instead, what he did, he says, I'm going to try using this technique on what we think was probably the core of another planet. And so he used meteorites, and he found that meteorites are roughly 4.55 billion years old. So 4,550, some million years old. So 4.5 billion years old, essentially. And so he gave us the first accurate age date on what we think is the age of the Earth, because the Earth and the planet or protoplanet that blew up or was torn apart around the orbit of Jupiter, near the orbit of Jupiter, that would have been about the same age. And so the solar system is roughly the same age from planet to planet to planet to planet, and so forth. And that was actually confirmed because we found that the age of the moon is roughly close to that. It's not quite that old. But and of course, the oldest rocks on Earth are not that old either. But we think that the Earth is roughly about that same age. So, okay, so on the next slide, we've got radiation. You guys probably have had some other science classes that have talked with you about this. You know that there's radio waves that are real long waves, and microwaves are roughly the size of a meter. Infrared or heat waves, essentially, right? And then there's the visible light spectrum, which you see shown here with all the colors and everything. And then ultraviolet is the next high energy step up from visible light. And then you can get into X-rays, which are pretty energetic and very short wavelength sort of rays that are emitted in the form of radiation. And then finally, you get into the gamma rays, which are the high energy sort of rays that are given off. And so they're showing you there the frequency, and then they're showing you the wavelength for these things as well. And so radiation is where energy is transferred from one thing to another. And so it goes up in energy states, perhaps because of that. So radioactivity is where certain atoms may be given off, or particles given off, or actually waves of energy are given off in a spontaneous sort of like radioactive decay event. And And when people take these sort of and measure these sort of like radioactive events, you have to have some sort of radioactive isotope. Now, I'm not going to go into what an isotope is now because I hope you already learned that before, if not in 110 in chemistry. But isotopes are atoms that have a variable number of neutrons in them. And because every atom of the same element has the same number of protons, it's the variety in the number of neutrons in it, pardon me, that makes it a radioactive isotope, if you will. So, for instance, when Claire Patterson was looking for something to date, he was going to use uranium-235 or uranium-238 in order to get his age dates. And then people have used also rubidium and strontium, and today they use a whole bunch of other species of radioactive elements that are capable of producing reliable age dates on some of this. So the chemistry explained in a handful of easy steps. Number one, you know that atoms are composed of a nucleus and an electron cloud. You know that a nucleus can have neutrons and protons in it. One of the simplest ones that we always show is helium because it has 2 protons and 2 neutrons. So protons have a positive charge, the neutrons have a neutral charge, and the electrons have a negative charge. Electrons essentially weigh nothing. They're very, very light particles, and we give a value of 1 to the protons and to the neutrons. So the atomic mass is actually just the number of protons in an element, whereas the atomic number is the number of protons plus the number of neutrons in the nucleus of an element. And so when you have a variable number of neutrons, those are isotopes. When you have a variable number of electrons, those are called ions. And so positively charged ions would have an excess number of positive of protons as opposed to electrons. And so electrons go in pairs usually. And so those pairs have to balance out with the charge on the nucleus, but they don't always. And because of that, we have certain ions and ionic bonding and things like that. And so those charges don't always balance out, but it's immaterial for the neutrons and for the atomic mass. The number of neutrons, less important until you get into the really large ones, and then they can spontaneously decay. So ionic bonding, occurs when you have pluses and minuses that are attracted to one another. So if you have an excess of plus charges, those are called cations. If you have an excess of minus charges in an element, those are going to be called anions. And so the cations tend to be the metals. So potassium tends to be, what is potassium is K, right? And so K, what is K? K is, you can have KCl, which is potassium chloride. So there's a +1 with potassium. There is a +1 with sodium. There's a +2 with calcium. So you get the idea. And so like iron, for instance, could be 2 or a +3 or a +4. So you get different sort of like elemental charges that go with each one of these sort of like neutrons or with the nuclei. And so those are the metals, those are the cations. And so the anions on the other side of Mendeleev's periodic chart, that would be like chlorine. Chlorine's a -1. And so you go down that column and all the -1s are like one step in from the far right column. The far right column are where it's all balanced, right? So that's your neon, argon, krypton, and so forth, xenon, and all the noble gases. And so they're all gases on the far right side. And so that's the story of why ionic bonding occurs. The pluses and the minuses come together, and sometimes you share the outer electrons in atoms that get close to one another, and you get covalent bonding. And so covalent bonding would be things like most of the silicates are covalently bonded. Now they do have some ionic bonding as well, so it's a ratio, and so not a ratio so much as there's a certain percentage that's ionic in the bonding with the silicates and a certain percentage that's more covalently bonded. So covalent bonding is where those electrons go around and kind of bind the entire compound together, if you will, the molecules that are formed of that compound. And so, okay, so when we get to radioactivity, we're usually talking about things that are pretty large. Most of them are pretty large in the nuclei. And so when you're looking at like uranium, there's 235 or 238 or some lesser amount in each one of those that will decay to something else at some point. So that's the radioactivity. So radioactive decay is when these things spontaneously break down into other sorts of substances, if you will. So there's 3 types of radioactive decay. Alpha particles are the easiest ones to understand. Essentially what it is, it's a helium nuclei that's expelled from, let's say, from uranium. And so an alpha decay would consist of 2 protons and 2 neutrons. And that particle is, even though it's very high energy, can be stopped by something like your hand. And so they can show you what can stop each one of those types of decay with number 1, number 2, number 3, and number 4 down here in the diagram. And so a alpha decay is just essentially a helium nuclei that's given off by the nucleus of uranium as it breaks down. The beta decay is where you get a transference that you can go from a neutron to a proton. And so you give off a particle in order to do that. And so the type of particle that you would give in that case is called a beta particle here. They're showing you an electron down here, but it could also be a positron perhaps. And so positrons have a positive charge, but they're just like an electron essentially. And so that's a beta particle. So it's still a particle, however, it's not just a wave. And so that particle could be stopped by maybe a sheet of paper, right? So that's the second, number 5 there that they're showing you there, or aluminum sheet, I guess it is there. And then lastly, there's alpha, beta, gamma, right? So A, B, C. Gamma is the C letter in the Greek alphabet. And so alpha, beta, and gamma are these high energy sort of waves that emanate, okay? And that's what happens when you get something that's a high quantum state going to a lower quantum state. It has an emission of a gamma ray. And so those are the 3 basic types of radiation. And there's things like neutrinos, for instance, that could go through the entire Earth, okay? And so, but they show you down here the things that can actually stop the radiation in these things. And so you have to kind of lead shield yourself in order to stop the gamma rays from actually penetrating your body and so forth. So gamma rays and X-rays, as you know, can go through the human body. Bones are pretty good at stopping the X-rays. And that radiation surrounds us everywhere. Okay, so how much radiation are we bathed in every day? Well, you get it from the sun every day. You're feeling the infrared, you're feeling ultraviolet, you're getting the suntan or whatever. All of that stuff affects us. There's no doubt about it. And we also get gamma rays. We get gamma rays from all around us, in fact. Not only from the sun, but we also get it from earth materials, right? And so the soils that are around us here, and even in the Ozarks, there's a lot of gamma radiation that's given off. And so, for instance, if you're around a granite's going to give off a lot of gamma radiation, maybe up to 400 counts per second, and that's in a square inch, okay? 1 square inch may have that many collisions with a gamma ray in 1 second. So it gets pretty high if you get some pure uranium, you're going to get some really high counts in 1 square inch. I've seen up to like 1,700 before in some radioactive materials. So, okay, so we have radioactive isotopes. And so on the next slide, you can actually see uranium-238's decay series. And so you take uranium-238, that's the very upper right-hand side here. The atomic number is 92. That's what makes uranium uranium, is by having 92 protons in it. But so the rest of, 238 minus 92, that's how many neutrons you have. And so with an alpha decay, you're losing 2 neutrons and you're losing 2 protons. And so you drop down to 234. There's 4 particles that depart, right? But also it's only two protons that leave. And so you're no longer going to be uranium once you give off that alpha particle. That alpha particle leaves and it spontaneously turns into thorium. And thorium, when it decays, it goes through a beta decay. And so the beta decays march over to the right-hand side. And so you can see when you have a beta decay, you're losing one of those protons and going to a neutron. And so you go to I think it's palladium. I'm not sure which that is. It's not palladium, I think, but it's Pa on there. It's not polonium, but it's polonium is 218 down here. You can see on the decay curve. Proactinium, I think that's what it is. So Pa 234, and Pa 234 goes to uranium 234. And so it can actually make the round trip back to uranium 234. Well, each one of these decays has a certain time interval that it takes for it to spontaneously decay in a stoichiometric way. And so you have first an alpha decay, and then a beta decay, and a beta decay, and an alpha decay, and an alpha decay, and an alpha, and finally you get down to lead 214 down here on the left-hand side. Not quite to the left-hand side, but you can see Pb or plumium 214 there. And then there's a whole variety, like a pachinko machine here, where you can get decays all the way down to, and the very last one is lead 206. And lead 206 is no longer radioactive and it's stable. And so all of that chain of different elements, that one atom can spontaneously go from the parent up in the upper right all the way down to lead 206. 82 is its atomic number. You can see down here at the very bottom. And so that's the radioactive decay for uranium-238. Okay, so that's good for uranium-238, but what about the other sorts of like decays that you can have? Well, you can have uranium-235 that also decays. And so what if you had the known radioactive decay rates for these elements? You could compare them to one another and you see where they cross over. In fact, you get what they call a concordance line, and that concordance diagram can give you some information about the age of the original material when it formed, okay? And that's from the uranium decay within probably a zircon crystal, a single zircon crystal. You can shoot a laser beam at it, you can ablate that crystal, and you get the information off of, it's usually in a ICP-MS, it's a inductively coupled plasma mass spectrometer, and you can find out the amount of uranium in that crystal. And you can even do it in zones of the crystal, okay? So you can do a transect across the single crystal in order to find out how much uranium and lead are in that crystal. Okay, so on the next slide here, you can see the actual length of time that it takes for each one of these to decay. So the highest one up there, uranium-238, is 4.5 times 10 to the 9th. In other words, it's the same age as the Earth, essentially, as the decay of one atom of uranium-238. Half of it would decay by 4.5 billion years. So in other words, how much uranium, original uranium from the formation of the Earth still exists? Well, it's going to be roughly half of that original amount is going to still be active in the environment today. And that gives us hope that we can still date other rocks, for instance. And so some of them are really short. So a few minutes for some and a few years for other ones. And so some of these are more important than other ones in order to get information on age dates. And so that whole process of trying to figure out the rates at which things decay, that's called a half-life. And half-life is actually just that. How long does it take for half of this radioactive substance to decay into the daughter products, to decay from a parent product to the daughter products that are the next in the step there? So uranium-238 is 4.468. I have the constant in the next page here. And eventually the product's going to be lead-206. And so when you do uranium-238, you're inferring that you're going to look at lead-206. When they do these sort of decay measuring these things, they often will get like lead 206, 209, I think it's 209, and lead 206, 208, and they get those ratios, and those ratios mean something as well because there are decay rates in between those as well, and it's a cross-check for how you go about understanding whether a system is enclosed or not, or sealed, where you're going to get a reliable age date. And that's what they use those ratios for. Okay, so one of the easiest ones to calculate for mostly archaeologists, is not something that's very commonly done in the geological sciences, although I have done it now, is getting a carbon-14 age date. And so carbon-14 has a half-life of 5,730 years, plus or minus 40 years. And there's a couple different ways you can do that. You can use a mass spectrometer. Well, they always use mass spectrometers, but you can use neutron activation sort of like technique, where you have to take it and you can use a very small amount and get an age date that's really pretty precise. So you can get back to 60,000 years with carbon-14. So carbon-14 is a funny sort of system, if you will. Carbon-14 is actually formed in the outer atmosphere. That carbon-14 heavy will fall to Earth and gets incorporated into living organisms. And as soon as something dies, it's no longer eating and ingesting carbon-14. So the carbon-14 that was in it when it died is the amount that stays with it then. And so you can measure old charcoal. You can measure, because the wood's no longer alive. And you can measure old seashells and things like that. And that's what I've done. I've got some ages of about 1,000 years based on carbon-14 age dates from some studies I've done in Jamaica, for instance, of some carbonate rocks that are down there. So anyway, carbon-14 is the one that they usually tell you about. So carbon-14, when it decays, doesn't go to other isotopes of carbon. It actually goes back to nitrogen. It's in the upper atmosphere as nitrogen, gets struck by a cosmic particle and turns it into carbon-14. Gets incorporated in living organisms, and then eventually it's going to decay back to that nitrogen. And so the carbon-14 that's left behind, of course, has a half-life. Otherwise, if you're beyond 60,000 years, you're not going to have any of it left, because it's all will have gone through, or very little of it left. It will have gone through radioactive decay. So what you see here in the bottom are a series of, like, what do you start with? The original amount, and you have the entirety of that substance there. If you have one half-life, only half of it's left. If you have two half-lives, you got a quarter of it left. If you have three half-lives, you've got an eighth of it left, and so forth. So 1/16 by the time you get to four half-lives. And then 1/32 once you get out there to five half-lives. And so in other words, as these substances break down, there's less and less the original material there. And so the spread gets a little bit wider when you get towards the limits. And so 1/16 of the original amount is still pretty good. So when you get out there with, like 1/256, maybe that becomes a little more suspect in how close you are to a valid age date. So that's carbon-14. And so you can see here what the half-lives are too in a diagrammatic sort of fashion. So what are the types that we actually use? So uranium-238, lead-206 is pretty good for any rocks that are over the 1 million years. It's good all the way back to the age of the Earth, in fact. Uranium-thorium is another one that's pretty good all the way back to about 500,000 years, but you can get as young as 75,000 years. There are lead-lead age dating techniques. Lead-210 is one that the USGS uses for sediments, coastal sediments. So you can get, with lead-210, because it only has a half-life of 22.3 years, you get relatively recent sedimentation rates that way. And then potassium-argon is an old sort of system that people use, but potassium has a half-life of, the radioactive potassium has a half-life of 1.26 billion years. Argon developed in the 1980s, I think. Rubidium, strontium, much older than that. Not commonly used anymore, that at least I'm not aware of. And then strontium. Strontium is mostly used in carbonates, because strontium can take the place of calcium in carbonate rocks. And so strontium is good for marine rocks, in fact. So strontium can be incorporated from seawater into marine seashells and so forth. Samarium neodymium is an unusual thing. Maybe you've seen these magnets that are, we call them rare earth element magnets, right? And so they're kind of oval in shape, and you can throw them up in the air and they'll buzz and make all these sort of funny tricks for you. That's a radioactive sort of substance, by the way. And so that neodymium and samarium that's used to make those magnets was originally released from the mantle. And so the samarium and neodymium, actually you can get what they call mantle separation ages. And so it's one of the few ways that you can actually date basalts. And you can actually discover what some of the oldest ocean crust is with samarium neodymium. And so we'll go into that in just a minute here. So radiocarbon is the one, of course, mostly with archaeology. But the other techniques that people use, and this is more common recently here, we can use beryllium and chlorine. You can take quartz grains and you can find out when they were last exposed. You can find out when they were last exposed to sunshine, essentially, with that sort of technique. It's called thermoluminescence. It's used in archaeology. It's used in Pleistocene age dates for sediments as well. Apatite fission tract dating is used if you have a known elevation and you have an igneous rock that's exposed at that known elevation. You can get the apatite crystals out of that, and you can count tracks, essentially, from cosmic particles that have intersected that crystal, cosmic particles that can penetrate through the rock, and they leave a little trackway behind, and it's a healed trackway, and you can count that, and you can find out when this thing was last raised up, essentially, or uplifted. Magnetic reversals, of course, are another technique, and I'm going to go into that a little bit more detail, so I won't talk about it right now. Oxygen isotopes can be used for dating somewhat. And then also dendrochronology, of course. And so you can count tree rings, essentially, to find out actual absolute age dates. And so on the next slide, I just want to show you some photographs of what it's like to date these rocks. Okay, so these are the oldest known substances on Earth are found in these rocks, and they're in they're actually in Western Australia, in the Jack Hills. And so the Jack Hills conglomerate here was a metamorphic, it's been metamorphosed. It's a conglomerate that was metamorphosed, but it was collected from the weathering debris from some of the oldest rocks on Earth, and it included some zircons. And so some of the zircons in the Jack Hills conglomerate, metaconglomerate, date all the way back to 4.4 billion years old, 4.4 billion years. And so that's right after the moon essentially was formed from that collision. That's when the igneous rocks formed and formed those zircons in that rock. And then that rock got uplifted, weathered, got deposited in a conglomerate, and then that conglomerate eventually got metamorphosed in some way. And today you can see it's upright, and it's been deformed somewhat even since then. So, but those are the oldest known substances on Earth, 4.4 billion years old. Some of the oldest rocks were found in northern and northwestern Canada, and it's an area called the Acasta Gneiss, and it's in the Northwest Territories. There were felsic blobs, if you will, in an ortho gneiss. Now, you know what gneiss is. That's that banded metamorphic rock, but in a few places there are chunks of granite that were in that were metamorphosed as well, but they were kind of shielded from all the metamorphic processes that reset a lot of the other age dates. Those dated back to 4.03. A fella named Sam Bowring here. So he was at MIT. So Sam Bowring passed away just recently here. He was a contemporary of some other folks that I knew at KU. But anyway, he found some of these oldest rocks at that time. Since then, there have been other old rocks, though, that have been found. So if we go on to the next slide, you can see the Acasta Gneiss here. And so when I talk about a granite protolith, I'm talking about the sort of like pinkish material that where the rock hammer is there in that photo on the right. And you can see some of the more gneissic sort of texture on the left-hand side over there. So, and then next you see some of the oldest rocks on Earth. Now this is on the continent, but those are basalts that were extruded and formed ancient ocean crust. And so when they did samarium neodymium age dates on that, they got back to, I think it was 4.28 billion years on these rocks. And it was very tough for me to to pronounce, but it's called Nunavut, I think it is. I'm not sure exactly how you pronounce it, but samarium neodymium ages on those rocks provided an age date of 4.28 billion years. That's when those rocks actually separated from the mantle, formed ocean crust. Okay, so on to the next slide. You can see zircon is the super mineral here. It gives you a little bit of information on it. It's very hard. It's very durable. It forms early, so it's easy to separate because of its high density as well. And so Dr. McKay here at Missouri State University does this sort of work, and he actually gets detrital zircons out of sandstones, for instance, and gets age dates on those, which he can maybe link up to different tectonic events. And so that's what the game is all about when it comes to looking at detrital zircons. And you can see where zircon is down here on the periodic table. So it's a pretty heavy metal to combine with that SiO4. So just a few more techniques to throw out here. The next slide shows you dendrochronology. It also shows you another technique here. There's a guy who's standing here with a student, and they're looking at different layers here. Each one of those layers actually represents a year. Now, this is one of the unusual exceptions in this sort of actual absolute age dating. And so with this, those are actually glaciogenic sediments. In far northern lakes, you get seasonality preserved. And so you see the light areas and then the dark areas. The dark areas are usually when you have ice over the top. And then when the summertime hits, you can get a lot of other sediment that gets deposited. And so each one of those represents a year. So dendrochronology is a lot the same. If you're looking at growth rings on a tree, you can tell how old the tree is. With varves, that's what these things are called in lake sediments here. Those things actually represent years too, just like on a tree ring. And then the next one is a slide that shows you how people have gone back and they've gotten different crons, if you will, out of the magnetic polarity of sediments. And so the magnetic polarity can be used to trace isochronous events, that is, equal time events, maybe across the basin or maybe across several basins. And so magnetic polarity is another way in which people can actually do absolute age dating. They can use that surface anyway as an absolute age date. And it may not give you an actual number. You still have to compare it to some other sort of radiometric age dating in order to get an accurate age date. But once you know where it flips from normal to reverse polarity, that surface then becomes really pretty important. So that's absolute age dating in a nutshell right here. So we're going to let it go at that, and I'm going to go on next to the next topic along on our list here. We're going to talk about the geologic timescale and how it came to be and all the people who contributed to it. So thanks a lot for your attention,